Okay, yeah, so now we're recording. Okay, yeah, so let's start. What were some ideas you guys had for this problem?
I started by substituting x equals y equals 0.
Good, yeah, so let's see. So first idea, let's try x equals y equals 0. That's always a good place to start. And let's see what happens. So we have, this will give us f of 0 equals 2 times f of 0 times f of a. Um, which means that f of a is equal to 1/2, right? Okay, so that's the first conclusion we can have. Um, okay, any ideas what to do from there?
Maybe x equals a and y equals 0.
Okay, so from x equals a, y equals 0, um, then we will have f of a equals f of a, f of a plus f of 0, f of 0. Um, but you see here, a is something fixed, right? So the point here is that when we say for some real number a, we don't know what it is, but it's fixed. So like whatever information we get from here, it will only apply to f of a. Does it make sense what I'm saying?
Yes.
Like from this, we can't really get any new info. Like we will see. Okay, well, like we will derive something we sort of already know. Does it make sense what I'm saying?
Okay, I think we can y equals 0.
Yeah. But Abdul, does it make I'm just trying to make sure like that you understand the statement, right? Like in this statement, a is something that like is really fixed.
Ah, okay.
Okay. Yeah. So you don't get to pick a or yeah. Yeah. Okay. So yeah. So Kareem's suggestion was that maybe we can just do just y equals 0, right? Um, so if you do just y equals 0, um, then we get what? F of x equals f of x, f of a, which is 1/2, plus um, f of 0, which is also 1/2, times f of um, a minus x, which tells us that f of x equals f of a minus x. Okay, so that's a very nice result. Your function is symmetric in some sense. Great, so what can we do from here?
We can rewrite the functional equation as fx plus y equals 2 f of x f of y.
Um, f of x, f of y. How did you get there? So you're saying we should just work with the original form, right? So yeah, I guess there's an observation here that this f of a minus x term appears in two places in the functional equation. So maybe we start with that. We say f of x plus y is actually f of x. I see, yes, f of x, f of y plus f of y, f of x. And so this is 2f of x, f of y, right? Great. Yeah, and so that's maybe a simpler form to work with. Great. And great. So now I'll make a remark that this is something that's like called a Cauchy type equation. So oh, can you see what I read? I think you can, right? Yeah. So this kind of equation is called a Cauchy type functional equation. So why do I say that? Yeah. So let me make some comments. So this is a general comment. Cauchy equations. So yeah, great. So usually Cauchy equation looks like this. Yeah, so so the one we found was like this. Right, so usually Cauchy equation looks like this, and the point here is what it means is that usually it tells us that f of x equals maybe cx for some constant c. And so what I mean usually is, okay, you need some conditions usually. So for example, if f is
Um,
for, yes?
I've read about this. So this is always this is always true for um cos equation over Q.
Uh-huh.
For over R, you need to prove continuity or boundedness.
That's right. So yeah, so that's the main point. So was
There
Kyle
is
and
also a condition, but in Eventions OTIS, but I couldn't understand it.
yeah, okay, so good. So yeah, so maybe I'll just repeat what Kareem said, which is that when you have this Cauchy functional equation, if it's from Q to Q, right, then you can really conclude that um, f of x is linear. And if it's not, uh, if it's say from R to R, you need some additional conditions. So maybe the additional condition is something like f should be increasing or f should be continuous. I mean, you'll have to really figure out from the context. But anyways, if you see this equation, it almost always means that f of x is linear. And then why is it related to this? It's because it can come up in a similar form, which is something like f of x plus y plus f of x times f of y. Okay. And the reason that is similar is because this is the same as log f of x plus y equals log f of x. Log f of x plus log f of y. And in this case, what you will almost what you will get is usually f of x equals c to the x. Okay. Yeah, that's right. Yeah. No, okay, let me see. Now, yeah. So that was maybe an aside, but let's go back to the original problem. So it was here, right? So we did some manipulation and we concluded that this is true. So what can we do from here? Yeah, any ideas?
Can we do the same thing with the log?
Yeah, great. So what do we do with the log? So maybe yeah, so let's try something like that. I need to make a new page. Okay, so let's maybe so let's try that. So let's try taking log. Now maybe I'll make some. You have to be careful when you do this, but if you know if f of x plus y, f of x, and f of maybe we just need f of x and f of y. If f of x and f of y are positive, then you can take the log. Otherwise you can't. But if that's true, then we get log f of x plus y equals log 2 plus log f of x plus log f of y. Okay. So what can we do from here?
Is it just Cauchy?
So it is Cauchy with this extra term, and I think what the extra term means is that log f of x is going to be c times x plus some other constant, maybe maybe minus log 2, I think is what it is, right? I think it means this, right? So okay, maybe we need to prove this, but at least we can guess something like this. Usually. But now, so I guess why am I writing this? So yeah, so still you need to prove something, but at least you can check what C has to be. What should C be by like plugging into something else? So for example, I think you can put it into the second one we have, right? So if you look at this one, right? So if you look at this relation, what does it tell us? It would tell us that cx minus log 2 equals c a minus x minus log 2, right? For all x, or maybe for most x, I don't know. So from here, actually, we can guess what c has to be. Yeah, there should only be one c, which will make this equation work.
Is it 0?
Yeah, so basically, I think we need c equals 0. So actually, what we want is log f of x. Yes, maybe I need some more space. Let's see. I think for this to really work, you need c equals 0, which means we should really have that log f of x equals minus log 2, which is the same thing as f of x equals 1/2, right? So okay, so that should be, I think, what. So that's maybe everything in blue and in red is maybe a guess, because in order to really use Cauchy's functional equation, you need some other condition. But nonetheless, it tells us that we should expect f of x equals 1/2. So any idea how we can really prove that and finish this problem? So we still have everything here, right? Everything in these three relations, we still have all of those we can use.
Hi, Tahsin.
Hi, Karam, how are you?
I'm good. Sorry for being late.
That's okay. Yeah,
Uh,
we're
I,
working. Mm-hmm.
yeah, I have an approach to prove that.
Oh, okay. You have a what?
An approach to prove f of x is equal to 1/2.
Okay, yes. What's your approach?
Yeah, I just 1 minute. Uh, uh, should I have a photo. Should I send it?
Yeah, you can send a photo.
Send,
Is it something? Can you explain? Maybe is it something you can? Is it maybe something you can explain, or?
uh, yeah, I can explain it.
Okay, yeah. So maybe you can tell us your first step from here.
Uh, we know that f of 0 is equal to f of x minus x. So, yeah.
Yeah. So f of 0.
Equal to f of x minus x.
So how did you get this? Yeah, maybe you can explain this.
No, x minus x is in the parentheses.
I see. Like this. I see.
Yeah.
Uh-huh.
So f of 0 is equal to f of x plus f of x times f of a plus x.
I see. So okay, I understand. Yeah.
Plus
Plus.
f of minus x times f of a minus x.
Okay, good. So this one is, I guess, well, yeah. So let's maybe explain what you're doing. So. Okay, so this one was, I guess, you plugged in y equals minus x, right? Or y
Yeah.
equals minus s. Yeah. Okay. Good. Okay, so this is y equals minus x.
Uh,
Mm-hmm.
f of a plus x equal f of a minus x.
F of a plus x. How did you get this one?
Because f of x equal to f of a minus x for all x for all x.
Uh,
So we plug x equal minus x.
uh, so you're using this equation here. Yeah, so if you use this one here, I don't think it gives us this, right?
I have a way to, we can prove f is cyclic. In our third equation, we plug in x and plus a.
So into which
Um,
equation? Maybe we
wait,
can.
x plus a, the third one.
The third one. So this one here. Oh no, Karam has. Okay, this one here.
Yes,
Uh-huh.
f of x plus a equals 2 f of x times f of a, and f of a equals half, so we could f of x plus a equals f of x.
Okay, and so then that will give us. I see. So then that
It's
one.
cyclic, and we can, so we can, yeah,
Uh-huh.
we can replace the second equation with f of x equals f of minus x.
I see. So then that gives us from these two, we will get
And I think we can complete the solution.
f of x equals f of minus x. Okay, and then what do we do? And so actually
Um,
that will give us as well what Karam was saying. Okay, and then what?
let's see, we can, right, we can plug in x and minus x and get f of 0 equals 2 f of x squared.
Okay, so we plug in x and minus x. Okay, so I guess we basically do this one here, and we'll get, so we get f of 0 equals
It'd be easier to just plug it in the third
go into third.
equation.
I see, into the third equation.
It should be the same, but
Yeah, okay, so into the third equation, so maybe into this one here, we plug in x equals x and y equals minus x. So we get f of 0 equals 2f of x squared. Okay, great.
so f x equals half or more.
Great. So yeah, so f of,
Equals 1 over 2 or minus 1 over 2 for each
okay,
x.
I see. Great. Great. And so now, good. So now we have to be careful. We
Uh,
don't.
I have a question. How did you know that? How did you get that f of x equal to f of minus x?
Yeah, good. So did you understand this line here?
Mhm.
So this one came, yeah, so maybe there's a lot of arrows. Maybe I can delete these arrows, but yeah, so basically the idea is for this one, that one came from this equation. So this equation, if you plug in y equals a, you get this. And that tells you that f is periodic. F of x plus a and f of x are the same. Does that make sense?
Um, but could you repeat that?
Yeah, so we use this equation. And in this equation, we put in y equals a. And
Yeah.
that gives us this. And so that tells us f of x plus a equals f of x.
Yes.
Okay, and then when we have f of x plus a equals f of x, and we also have f of x equals f of a minus x, we together get f of x equals minus x.
Yeah, so f of a minus x equal to f of a minus x plus a, which is equal to x. Or no?
So the idea, yeah. So it's periodic with period a, right? So maybe we can break this down a little bit. So uh, so what do we have? So we have this one. So from here, if we plug in what? So now we have f of x equals f of a minus x, but that's equal to f of minus x.
Yeah, I got it.
Okay, good. Okay, good. So that's that. And then I guess the next thing we did was we went from f of x plus y equals 2f of x f of y, and we plugged in y equals minus x, and it told us f of 0 equals 2f of x squared, which tells us f of x equals 1/2 or minus 1/2. But again, we have to be careful here because it doesn't mean that you know, there's two solutions. It means we need to like decide for every x which one it's true. Yeah, does
Yeah,
it make sense?
the pointwise trap
That's right. So yeah,
eventually works.
right. So yeah, maybe we
Also,
can.
I
So
think
this.
we can do it easily by plugging in x and by plugging in y equals x in the third equation.
So yeah, okay. So, but okay, before we go on, does it make sense why we're not done? Okay. So this is like, I just want to make this to emphasize this. We're not done with the problem, right? Because it doesn't mean there's two solutions. We need to like it could be there is still infinite solutions. Does that make sense what I'm saying?
Yeah.
Okay. Okay, good. So then your idea for resolving it was what, Kareem?
Uh, we substitute y equals x in the last equation.
Okay, so in the last equation, by the way,
The third one, x
okay,
plus y equals 2.
great. So yeah, so we look at this equation and we plug in y equals x. Was that it? Yeah. Okay, so and we put in x equals y, and so we get f of was it x equals y you wanted?
Uh, doesn't matter.
Okay. Okay, and right. So why does this solve everything? Because this one actually, no matter what, is positive, right? So this is actually 1/2, no matter what. And so then we're done, right? Because this is true for all x. Uh, does that make sense? Okay, so any comments or questions on this problem? Okay, so let's maybe go to the next one. So now we wanted to look at number 10 on the homework, right? So this is question 10. And now we want to function from positive real numbers to real numbers. And it should have three properties. So first we want 2 times f of x plus f of y equals f of x plus y plus f of x minus y for all x and y such that x is greater than y. Okay. And it looks like, okay, maybe I'll make a comment about, so this kind of condition, x greater than y, is kind of strange. It's so that this term here makes sense. That's why they put it there. Second condition is f for f of x, f of y equals f of 2xy. And the final condition is that f is increasing. Okay, so these are the 3 conditions. So where do we begin? Right. So usually the 2 things you're doing when you begin are you are either plugging things in. So go right A, plug in values, and B, guess the solution. Right. So any ideas how to begin?
We can plug the first equation, y equals 0.
Okay, so let's put in y equals 0 into, maybe let's label them. So this is equation 1, equation 2, okay, and equation 1. So this will tell us 2f of x plus 2 f of 0 equals equals 2f of x. Good, and so that will tell us that f of 0 equals 0. So that's a good thing to know. Okay, what do we do next? But maybe but let me actually just let's make a comment here. We actually can't do that here. Do you see?
Right. Because
Yeah,
positive fraction.
yes,
Yeah.
yeah. Good. So that's a good because I didn't realize, but yeah. So this actually is not allowed because it's only here. So that's a good point. We can't use f of 0 for this problem. Okay. Any other suggestions?
In the second equation, we can use x equals y equals 1, maybe. Oh, no, never mind.
Well, I mean, let's maybe just put it
Uh,
in. Yeah,
how about x equals 1 over 2? Second equation.
x equals 1/2. Great. So yeah, I guess the point there was we saw this, maybe we want this 2x to be equal to 1, right? Right. So x equals 1/2 in equation 2. And then we'll get 4 times f of 1/2 times f of y equals f of y. So that's very useful. It almost tells us that f of 1/2 equals 1/4. But it really tells us is that there are 2 possibilities. It tells us f of 1/2 equals 1/4, or f of y equals 0 for all y. So the second, thing is kind of boring, but certainly it works. So let's keep that in mind. So yeah, so certainly put in purple. Certainly this is a solution to the whole. Actually it's not. Do you guys see why this f of y equals 0 is not a solution?
Because f is increasing.
Yeah, so it's actually not a solution because of this increasing business. So we can actually discard it because of increasing. And so that means we certainly know this is true. Great, so f of 1/2 is 1/4. Okay, great. So what else do we have now? What can we do now? So we plugged in many values. Any idea how to guess the solution? Can anyone guess the? Maybe I'll point something out, right? There's this, the second one is actually another Cauchy equation. Do you guys see how? Or it's almost. I mean, it's yeah. I would consider that this one as well to be a Cauchy equation. Do you guys understand why it's a Cauchy equation? So
Yeah, we can do the same thing with the log as before.
right. So if we do it with the log, so maybe this is an aside. So if I have something like this, I will ignore. For now, I will ignore the 4 and the 2. But if you take log, you get log f of x plus log f of y equals log f of xy. Right? So it's not quite the same, right? Because remember, what was Cauchy? Cauchy was this guy, right? F of x plus y equals f of x plus f of y. Here we're getting f of x plus f of y equals f of x times y. So it's not exactly the same. But what you can do is you can say x equals e to the u, y equals e to the v, right? And e was arbitrary. I just wanted something. And then actually, in this case, we can do that honestly because this is a x and y are positive. So you can honestly do this. And then this equation actually becomes log f of e to the u plus log um, f of e to the v equals log f of e to the u plus v, right? So now it's really Cauchy, this Cauchy equation, right? Does that make sense? Does it make sense what I've done here? Hello, can you guys yeah,
Okay, I think I got it now.
okay, yes. Yeah, I'm saying it's Cauchy, but with maybe with the function g of u equals log of f of e to the u. And so why do I bring this up? This will help us. This should give you some idea of how to guess the solution, right? So the point is Cauchy should be linear, right? So let's look at what that means. So from all of this, we get something like log of f of e to the u. We are guessing is something like a constant times u. Right, so maybe this is a guess, so maybe I'll write it in blue. So guess is that log of but okay, maybe we should sort of be careful. It's not exactly that. It's a little bit different for us. So for us, we have log of 4 plus log of f of e to the u plus log of f of e to the v is equal to log of f of e to the log 2 plus u plus v. Okay. But okay, all of this is to say that what we should have is something like log of f of e to the u is something like cu plus d, right? It should be some kind of linear thing. Does it make sense where I've gotten this from?
Yeah.
Yeah. Kareem and Karam, do you guys understand what I'm saying?
Actually, I don't know what is Cauchy equation.
So this Cauchy equation is something that happens a lot in functional equations, right? So the first example is this one. If you see something like this, okay,
Yeah.
f of x plus y equals f of x plus f of y. And so the point is the solution to this is usually f of x equals c times x. Okay. And maybe I'll assign it as homework. But for example, if your function is from rationals to rationals, then it's true. You can do it by induction. And if it's not, if it's from R to R,
Um,
it's usually true, but you need some more conditions.
yeah.
Okay. And
How can we do it by induction?
so the idea is, yeah, so how do you do it by induction? That's a good question. So first you do it for the integers, right? So first I say, okay, f of 0 equals 0 because I plug in x equals y equals 0. And then you say, okay, f of 1 equals c, f of 2 equals c plus c equals 2c, and so on. So you get it for there. Does that make sense? That tells you for the
Yeah.
integer. And then you say, okay, what about f of, say, 1 equals f of 1/2 plus f of 1/2, right? So that tells you that f of 1/2 is c over 2. Does that make sense? Karam, does that make sense?
Yeah.
Yeah. And then maybe you say f of 1 equals f of 1/3 plus f of 1/3 plus f of 1/3. And then that tells you f of 1/3 equals c over 3, and then so on. Does it make sense?
Yes.
Yeah, it's yeah, that's how you do it for the rationals. And so the point is you can't do this for the reals. So usually for the reals you need some other condition. But yeah, so we'll discuss, I think in this problem it will show up. But yeah, I guess what I'm saying is the following. This one here is actually very similar to Cauchy. Whenever you see something like this, you should think it's very similar to Cauchy, and it's because you can do something like this. Yeah. Does it make sense what I've gotten here?
Yes.
Good. And so what is the point of all of this? It means that f of x should end up being something like should be some constant we need to determine times x to some power. Right? Yeah, maybe I'll write c for the constant. So it should be, in the end, it should be c times x to some power. Yeah. Okay. So that should at least be our guess. And then can you figure out in this case what c and r should be?
Maybe R is maybe -2 or 2.
And so where are you getting this one from?
It's not. It's just a speculation. Like
Oh, I see.
because 1/4.
Oh, I see. Yeah, right, because of this one, right? Oh, I see. It's coming from here, right? Yeah. So yeah, I guess then you would need r equals 2. Um, yeah, I guess you can. One thing you can do, you can just plug it into this equation, but that's kind of, yeah. What do we get if we do that? So from equation 2, maybe we can just solve. So from, let's see, equation 2 will tell us that 4 times c squared times x to the r y to the r equals c times 2 to the r x to the r y to the r. So we have 4 times c equals 2 to the r. Okay, I mean, this is kind of not, this is not that helpful. But okay, maybe I'll say this. I think if you think about this equation, maybe you can figure out which one it is. Yeah, okay, so so Abdullah, you made this comment, maybe r is 2 or minus 2. I think out of
Yeah.
these, only one of them will work for the first equation. Right, so
Oh yeah, which is 2.
yeah, so I think, you can, maybe it's a reason you can guess at least, but so if you take, yeah, if you take f of x equals x squared, it actually satisfies the first equation. So that's a good guess for what the answer is. But yeah, so any idea how to actually to solve this? So far we have f of 1 half equals 1/4, and we have some guesses. We have f of x equals x squared is the guess. So any idea what we can do? So what I'll say is this. So let's first gather all the information we have. Um, so so the information we have is that, okay, f of 1 half is 1/4, and we have a guess, which is f of x equals x squared. So now what I think, yeah, what is often a good idea to do at this stage is to just start gathering information about f, right? So I mean, whatever you can learn. I don't know.
Can we maybe combine the two equations in a way that's helpful to us?
Okay, so equation 1 and equation 2.
Yeah.
Yeah, do you have any ideas how to combine them?
Um, I'm not sure. I'm not sure.
Um, yeah, okay, so maybe I'll say what is can yeah, so maybe I'll say we've plugged in some values, we've guessed the solution. I think what we do is just gather information. So maybe I'll ask the question, is there any value of f that you can determine other than 1 half? Okay. Yeah. Let's think. Mm, let's see.
What if we plug in the second equation, y equals a half?
So I think that's how.
Or,
So I
oh
think
yeah,
that's
yeah,
how.
it's not.
No, I think that's how we
Yeah,
got
yeah,
this.
yeah. I see, I
Yeah.
see.
Yeah. Yeah. So now I'm trying to think. How do we actually solve this? Um. Yeah. So I'm wondering if we can get f of 1. I think that would be a helpful one to have. Let's see. Um, let's see. So let's see. So we have maybe from equation 1, we get 2. Sorry, this pen is getting loose. 2f of x plus 2f of 1 equals f of x plus 1 plus f of x minus 1. So if we knew f of 1, we can actually get f of any integer. Um, is there a way to get f of 1? Um, hmm. Hmm. And then for equation 2, we can get 4f of 1 squared equals f of 2, but that's not that useful. Yeah, and maybe we can do this. We can say, yeah, so maybe I'll say what I'm saying. So what I'm trying to get f of 1 equals 1. So what we want, right? What we want is that f of 1 equals 1. Because if we can get that, then we can actually get a lot. We can actually get f of any integer. And now, what is the strategy for getting f of 1 equals 1? I think you can say this. So you can say from equation 2, we have 4f of 1 squared equals f of 2, and 4f of 2 squared equals f of 4, which together gives you f of 4 equals what? 64 times f of 1 to the 4. Is that right? Now, why do I bring that up? Is because so that's from equation 1, but from equation 2, you can also get f of 4 in terms of f of 1, right? Because now I can say, what can I say? I can say, so yeah, I can say 2 f of 2 plus 2 f of 1 equals f of 3 plus f of 1, and 2 f of 3 plus 2 f of 1 equals f of 4 plus f of 2, right? And these two together should give me f of 4 in terms of f of 1. And yeah, what does it equal? Let's see, so yeah, maybe we need more space for this. So yeah, let's make a new page. So the idea here is so what I want is this from equation 1. Rather from equation 2. So from equation 2, we got this much. And then from equation 1, so I wrote you two, I meant 1. From equation 1, we have this. And yeah, so what does this give us? This is f of 3 plus f of 1. And so 2f of 2 plus 2f of 1 plus f of 3 plus f of 1 and 2f of 3. So this will give us now f of 4 equals 2f of 1 minus f of 2, which is 4f of 1 squared, plus 2f of 3, which is equal to f of 3 is f of 1 plus 2f of 2. So this is it's equal to 2f of 1. Maybe no, let's be careful. So 2f of 3 is 2f of 1, so 4f of 1 plus 4f of 2, so plus 3f of 2, which is 12f of 1 squared, I think, right? And so we get 64 f of 1 squared to the 4 equals did I make a mistake? So are you guys following the idea here? Do you guys understand the idea? There should be a strategy for calculating f of 1.
Yes.
Yeah, but somehow I'm not, I think I'm making a mistake somewhere. Hmm. Hmm. This doesn't give me what I want. Um, okay, does anyone know how to where my mistake is? Because I've definitely made a mistake, right? Hmm. It's here actually. This equation is wrong, right? Yeah, this equation should actually say what? It should say 4 f of 2 f of 1 is equal to f of 4, right? And that means f of 4 is actually equal to 16 times f of 1 cubed. And now we get this equation. Okay. So this is what we should have. Yeah. Does it make sense?
Yes.
Yeah. Um, Abdullah Karam, have you guys followed this calculation?
Yep.
Yeah, we are following.
Okay, good. So now what does this? So now what do we do with this?
Maybe vectoring 4f of 1.
Yeah, right. So now what do we do from here? So yeah, good. So now maybe we can erase all of this. Point of all of this is that now we have what? 16 f of 1 cubed equals 12 f of 1 squared plus 4 f of 1. So what are the possible values for f of 1? Let's write f of 1 equals maybe r. So we have 16r cubed minus 12r squared minus 4r equals 0. And I think, what is it? Says r and r minus 1 are solutions, and then the other one should be maybe minus 1 over 4, I think. Yeah, so I think it should be r equals 0, 1, and minus 1 over 4. Yeah, because what does it mean? If we have 16r squared minus 12r minus 4 equals 0, the sum of the product of the roots is minus 1 over 4, right? So these are the possible values.
And
Since
since
f
it's increasing, we can just take one. It's the only option.
That's right, yes. Now we use increasing to get, yeah, good. Yeah. Because increasing. Great. Okay, so that was a lot of work to get one value of f, but maybe it will be useful because now we have two values of f, right? So we have um, so now what can we do? So good. So yeah, let's just remind. So what was the point of getting f of 1 equals 1? Because then once you have f of 1 equals 1, um, so f of 1 equals 1 plus induction and equation 1, I think should give us f of n equals n for, was it n or maybe n squared for integer n. So do you guys understand this one? Yeah, let me, I
Yeah.
think the point, yeah, okay. Is it okay? You need to check it, but I mean, it should work, right?
Mm-hmm.
Okay, so now what do we do?
So now we try to generalize for rationals, real numbers. Sorry.
Right, so yeah, so we do, right, so this is a good, so you said rationals for, so we want to do it for all reals, but I think you're right, it's easier to do for, maybe it should be easier to do for rationals, I think. Maybe we can, let's see. Um, because once you have it for rationals, the last condition will give it to you for all reals. Okay, so let's see if we can do it. Yes, any ideas what we can do?
I was thinking of taking g of x equals square root of x and trying to prove that it satisfies Cauchy, because then we can, since it's bounded, since you can just uh, um, put y equals x in the second equation, we know that it's that f of x is greater than or equal to 0.
Was
Uh,
it is it g of x? It's square root of f of x. Is this what we want?
Square root of f of x.
Yeah, okay, there we go. So square root of f of x. Good.
So if we prove it satisfies Cauchy, we should be done.
Good. So one strategy. So yeah, maybe I'll make this one. So so one strategy can be show g of x equals square root of x is Cauchy. Yeah. So one idea is maybe we can take the square root of equation 2. So then what? Then we get 2 g of x, g of y equals g of uh, 2xy. Um, hmm. Hmm. So yeah, so one point comment I'll make is hmm, it's very hard. It's I mean what will happen then is like these equations, right? So if you make the substitution, these equations become something like 2 of g of x squared plus g of y squared um, equals g of x plus y squared plus g of x minus y squared, right? So it's kind of and it becomes very hard to work with. But maybe I'll make some comment, right? You know, this second equation is not it's not exactly Cauchy, but it's very close to being Cauchy, right? So what you can do is you can borrow a lot of the ideas from the Cauchy equation. So from the Cauchy equation, what's the idea? First you know you get f for integers, and then you get f for like rationals, right? So here's something I think you can do. I think you can look at this equation and it what? If you plug in y equals 1, right? So let's write something here. So if I look at this equation and I put y equals 1, I'll get 4f of x equals f of 2x. And so actually what it means is once I know f of say yeah, so I'm using that we have this one here. But now if you have f of 1, for example, you can get f of a half, f of 1/4, f of 1/8, and so on, right? And why do I think that's useful? Because once you have, say, so using this, you can get f of 1 over 2 to the n is, I think, whatever it's supposed to be. And then you can actually put that into here to get f of k over 2 to the n by induction, I think. Right? Is that right?
I have a suggestion.
Uh-huh.
Can we just substitute in the second equation, we can put f of 2xy equals 4f of xy, and then dividing by 4, we get f of x times f of y equals f of xy. This could be easier to work with.
Uh, um, sorry, so can you say the suggestion again?
F of 2xy equals 4 f of xy, and second equation,
Uh-huh.
and we divide by 4. It would be easier to work with.
So you're saying, so are we saying one
F of
fourth
x.
like this, or am I saying?
Uh, yeah, but we could just write it as f x of y equals f of xy.
You're saying this is equal to f of xy?
Yes, because of what you wrote after we yeah.
Yes.
Yeah.
Yes, great. So yeah, from very good, right, very good. So we can take, very good. So we can take this one. Very good. So we can take this one, and then we can get this, right? Great. So yeah, very good, very good. So that tells us now that f of xy equals f of x, f of y. Okay, very good. Good. Yeah, so now we
I
really
have
have.
a
Mhm.
Yeah, I have a question about the if you wanted to show that g of x equals square root of f of x is Cauchy, right? So
Yeah,
don't we have to prove first that f of x is positive or non-negative?
that's right. That's right. You do. Yeah. So I think Kareem's suggestion was something about general strategy, right? So um, yeah, but yeah, you're right. It's a good comment that if you ever want to take the squared, you have to prove that something is non-negative. Um, but anyways, I think already we can sort of, I think what Kareem's argument has shown is that f itself is actually Cauchy, right? Right, or almost Cauchy. It's multiplicative Cauchy. But what is the point? Once you have this, right? So this is maybe we could call it multiplicative Cauchy. You're actually you know you're done, right? Because yeah, maybe I'll yeah, let's maybe I'll make a new page for this, but actually I think at this point we're done with the problem. So no, that's not what I have to do. So now, so what's the idea? I think we're actually completely done from these two observations, right? So what do we have? We have number one, f of xy equals f of x, f of y. And number two, we have f is increasing. And maybe also number three, we have f of 1/2 equals 1/4. And yeah, okay. Why is that? So yeah, good. So why are we done? So let's yeah, the reason we're done is if we could say g of x equals log of f of e to the x, then g of x plus y equals g of x plus g of y. Does that make sense? This was the first sort of the first idea at the sort of. Does this make sense? What I've written here?
Yep.
Yes.
So the only thing we need to do, and moreover, if this was true, it would be true that g is also increasing, right? Because e to the x and log are both increasing functions. So plus g is increasing. So together these would give that g of x is linear, right? And then you can use this third condition to figure out what it really is. So the only thing we have to do is we need to actually argue that this is a valid thing to do. And what that means, we have to show that f is always positive, right? F of x is always positive. Does that make
Um,
sense?
yeah.
Yeah. So any idea to show that f is always positive?
Y equals x, second equation.
Second equation, if you put y equals x, great, we get f of 2x. Yeah, great. So from the second equation, if we put y equals x, we'll just get we'll get 4f of x squared equals f of 2x squared. And since 2x squared can be anything, it will tell us that
Wait,
the
yeah.
yeah, and yeah, good. So then we get f of x is positive. Does that make sense? Maybe
Yep.
strictly what it tells us f of 2x squared is positive, and that can be anything. Okay, so does the solution make sense to maybe okay, sure, maybe I can just recap what the ideas were, right? So what was the idea? So yeah, so we first needed this f of 1/2 equals 1/4, and then we needed f of 1 equals 1, which we got from plugging in some small values. And then from there, okay, maybe it's then from there you can get this multiplicative Cauchy, and then you actually know what to do. Yeah. Is there any questions on this problem?
How do you know that g of x plus y equal to g of x plus g of y?
Ah, great. Yeah, so this is maybe something I wrote before. Maybe I can just write it again. Maybe I have lost it somewhere. Okay, I don't see it anywhere, so let's just derive it again. What's the idea? So maybe I can just start a new page actually. So, right, so what's the idea? You have something like f of xy equals f of x, f of y. So this is a multiplicative Cauchy. And we make the substitution g of x equals log of f of e to the x. And now we want to show that g is actually Cauchy. And so what do we do? Well, we take this one. And so this is, we take log of both sides. We get log of f of xy equals log of f of x plus log of f of y. And now this is equal to, this is the same as saying log of, yeah, maybe let's write something. Let's write x equals e to the u, y equals e to the v, log of f of e to the u plus v was log of f of e to the u was log of f of e to the v. And so this is saying g of u plus v equals g of u plus g of v. Does that make sense, Carl?
Yeah, thank you.
Yeah, good. Yeah. Good. So yeah, so you should, I mean, there's like 3 or 4 variants of this Cauchy equation. You should know all of them. Okay, great. So let's do, maybe we have time for one more. Yeah, okay, maybe we can do one more problem. So let's see. I wanted to, actually, there was one problem I wanted to do that was not on the homework because I think it illustrates some good ideas. There's actually 2 I wanted to do. Yeah, so maybe we can do. Okay, yeah, there's one problem I wanted to do, so maybe I can do this one. By the way, we're almost out of time. Is it okay if we go 15 minutes over time? Is that okay for everyone?
Yes.
Yeah.
Yeah, okay, good. So, because I wanted to do this problem. So the problem is like this. You have function from R to R, and so this is the problem. Maybe let's take 5 minutes just to think about it. See if we have any ideas. Yeah, so in 5 minutes I'll ask for some ideas.
Yeah, I think I saw this one before in OTIS excerpts
I was
event.
just gonna say, yeah,
Oh, you guys know this one.
Yes.
I've seen it. Yeah, the book of event trends.
Ah, I see. Okay, so you guys have cited. So would it be useful to go over this one, or is it? Yeah. So I mean, yeah. Would it be useful to go over it, or maybe we can skip it? I'm not sure.
Yeah, I think we can skip it.
Yeah. Okay. Good. Okay. So
Yeah,
maybe.
yeah, you just prove it's an involution and
Yeah. Okay. Good. Okay. So maybe you guys already know the idea. So maybe we can move. Um. Maybe I'll. Okay. In that case, what can we do? Maybe we can do the last problem. Remember number 11? Maybe that would be. Yeah. Maybe we can look at problem 11. So. Okay. So this is problem 11 from the homework. So you want to function from positive rationals to positive rationals such that um, f of x, f of y is f of x over y. Okay, so what's the idea here? Um, hmm. Yeah, okay, so what were did anyone have any observations for this one?
um, can we prove it's a bijection?
Ah, how did you do that?
Um, First of all, um, we have the solution of x equals 0, but suppose not. Suppose suppose not. We choose some x such that let's call it x0 or something different. Such
Yeah,
that f of x0 doesn't equal 0.
I see, so
And then
suppose. Okay, great.
right, then we can put y equals some term that depends on f of y. And I think we can prove it's a bijection.
So I don't understand. So we're saying y equals
Equals f of x0 divided by f of x times f of y.
like this?
No, the denominator should be the left-hand side of
I
the
see.
original equation.
The like this like, is something I'm not understanding. So f of y equals what?
Um, you just plug in x0, x equals x0, and in the original equation.
Ah, okay, x equals x0.
Uh,
Um,
and
and then f of x0, f of y is equal to f of x0 over y. Yeah, but then and then what?
and then I want to write as y equals f of x0 divided by f of x0 times f of y.
Like this?
Yes.
Ah, I see. Okay, and then so then what happens? Then we are saying, okay, this is
Um,
very clever. So then we are getting f of
um,
x0 times. Am I understanding this correctly? No, but I'm a little confused.
um, not sure what you did, but um, I was thinking that we can prove it's an It's a bijection because we can get any y using by homology changing f of y.
I see. Your point is,
Yeah, since it's different for any two y, then f of x 0, f of y should be different for any two different y, and so f of y is different for any two y, meaning it's surjective, and
I see. So, I
um,
see. Okay,
yeah.
so we're trying to show, so okay, we want to show that it's a bijection. And so for surjective, you're saying, I understand what you're saying. Uh, you're saying, f of x naught over y can take any value. So that means it's surjective. And now for injective, what is your argument?
I think we could use the same thing.
I see. So you're saying, if f of x non, I see. You're saying if f of a equals f of b, then we say a equals x naught times f of y1, and b equals x naught times f of y2. Is that right? And then because it's surjective, we can do this. And then no, am I correct? And then we're saying that, and then that tells us that that tells us
y1
x,
equals y2.
yeah, okay, great. y1 equals y2, and then that tells us that a equals b. Okay, good. Okay, very good. Does the argument make sense to everyone?
Yeah.
Yeah, okay, that's very clever, Kareem. Yeah, I'm not, it's a very clever argument. Good. So we know it's good. So now we know it's really, we know it's bijective. So now what do we do?
Maybe you can plug in y equals 1, and then since it's a bijection, then x f of 1 must be equal to x.
Uh, okay, let's just, yeah, let's write this out. So can duplicate. Okay, so now we want, so we have it's a bijection. So let's we can erase this argument here. So so then f is a bijection. Okay, then Abdullah, what was your suggestion?
Plug in y equals 1, and since it's a bijection, then x f of 1 must be equal to x.
Right, so then x. So that tells us f of 1 equals 1. Great, very nice. Oh, maybe I'll let's just recall what maybe I'll make some comment, which is, well, let's recall this question is not to find all of them. It's, is there such a function? Right. So yeah. So this is from this is problem 11 on the homework, and problem 11 on the homework is not to find all such functions, but it's to find at least one, or show that there are none. Yeah. So I guess soon we'll either to conclude that there's none, or we'll be able to construct one. Okay. So any ideas how to go from here? Yes, I guess we're in the stage where we're trying to gather information, right? So there are other values of f we can determine.
Maybe plug in x equals 1 now, and now we know f of 1 equals 1. So f of y equals 1 over y.
No, oh, sorry, that's right. Yeah, I made a mistake. So f of y equals 1 over y. Great. Okay. Very nice. Good. So this is a very strong piece of information that we have, these two pieces. Okay, now what can we do?
Maybe we take f of left-hand side and f of right-hand side.
So you want to write like this? Like this? Oh,
And the final equation we got f of y equals 1 divided by y.
wait, sorry, I didn't understand.
In the I want to do this in the final equation we
Ah,
got.
I understand. Okay, so you want to work with this one.
Yes.
I see. Now you want to say f of y equals f of 1 over y, like this.
Yes.
Good. So what does that tell us? But now, yeah, so what can we do from here? Yeah, I mean we can make this guy 1 over y, but I'm not, yeah, then we just, it's okay.
We can make left-hand side equal to 1 divided by f of y.
Yes, we can do that. Good. And so that tells us that f of 1 over y equals 1 divided by f of y, right? Hmm. Hmm. Any ideas? Hmm. So I wonder if we can maybe rewrite this equation a little bit more nicely with all this. Yeah, so we have a lot of information from these two, right? So maybe we can rewrite this one a little bit better. Yeah, so maybe we can say
If we substitute y equals f of y, we can get f of x over y equals f of x all over y.
yeah, so maybe can you explain one more time?
In the first equation, you can substitute y equals f of y.
Okay. Maybe we can say okay.
Or y or f of y 0 or something.
Yeah. Okay.
Anything.
Or maybe f of z or something. I don't know. Maybe we can say okay. Y equals f of z. I'm not. Yeah. Okay. And then what do you
Yeah,
say?
yeah. Then
Mm-hmm.
it becomes f of x over z
Mm-hmm.
is then equal f of x z, I think. Wait.
Maybe over f of z or something. Yeah. So let's again. Let's do the whole thing. So it's okay. It's f of x times f of z. But this one is equal to f of x over z. And this is equal to f of x divided by f of z, right? So I think that's what we get. F of x over z equals f of x over f of z. But actually, I think, then if you say maybe z equals 1 over w or something, right? Then this becomes f of x w equals f of x f of w. Is that,
Yeah.
yeah. So actually, we're back to this multiplicative Cauchy. So now let's, yeah, so now what's the point? So yeah, so this is a good example to understand. We have this multiplicative Cauchy, but it's not from R to R, right? And it's not increasing, so it's kind of strange, right? So yeah, let me sort of make a point here. I think I'll use a new page. So this is a really important thing to understand. So if we have the regular Cauchy, right? And we are say from Q to Q, basically you can show by induction. What does this show? By induction, f of x equals a constant times x. Or if you have from R to R and say increasing or some kind of thing, I don't know, you'll also get f of x equals cx, right? You need some extra condition. On the other hand, for multiplicative Cauchy, okay, let's say it's from R positive to R, then so and say it's increasing, then we get, okay, maybe we get something f of x equals x to the R for something. Okay, we can show that, but it's a little bit different if it's from Q to Q. Okay, so what now when we talk about multiplicative Cauchy, let's say Q positive, right? From Q to Q, this is a bit of a different equation. It's actually the flavor is very different from all the other ones. So can someone maybe tell me what is the general solution going to be for this kind of thing?
F of x is cx.
Well, so that won't work, right? If f of x equals cx, I mean, that won't work here, right?
For this one,
Yeah.
x to the power of r.
Yeah, so that will work. I guess r has to be, in this case, it should be an integer, right? Because it's from rationals to rationals. Although even we can do to reals, it's okay. We can do to r here, and then we can say x to the r. But there will actually be more solutions in this case. If the domain is just positive rationals. And the way you should think about this, you should think of, this last case is really some kind of number theory thing. Because what you do is you take your number, you take x and you write it as P1, E1, P2, E2, P3, E3, and so on. Where P1, P2, P3 are the primes, and the exponents can be positive or negative. Does it make sense what I'm saying? So like if you wrote 5 over 6 would be 2 to the minus 1, 3 to the minus 1, 5 to the 1. And then the idea is f of x is equal to f of p1 to the e1, f of p2 to the e2, f of p3 to the e3, and so on. And this is actually a general solution. You can actually choose f of p1, f of p2, and so on. These can be completely free. Does it make sense what I'm saying? Like I'm saying there can be some completely wild solutions. Like you can have f of 2 equals 7, f of 3 equals um, you know, 1/2, and then f of p equals 1 for all other primes. And that will be a completely valid solution. Does it make sense what I'm saying?
Why is that the case? Why?
No, I'm saying this is an example solution. Like, do you see, like, do you understand this is a possible solution?
Yeah.
And then, but now every solution is of this form because you need to tell me what the function is at prime numbers, and then you can determine its value everywhere else using the multiplicative property.
Oh, I mean, why does it have to be this form? Like, why can't it be in another form?
So I guess what I'm saying is f of p1, f of p2, like these numbers determine f. They
Okay,
deter
I see the point here. Okay, I see it.
they determine f because I mean you can think about this equation, right? But that's what this equation will tell you.
Okay, yeah. I get it. Yeah.
Yeah. So that's the important point. So actually, there's some, sort of not that big, but still very big class of functions that satisfy this if I only require the domain to be positive rational. Does it, Karim, does it make sense?
Yeah.
Yeah, so I wanted to make this aside, which is just, sometimes you have to, when you see these Cauchy type things, you have to be careful. And so in our situation, where are we? So where are we? Yeah, so we are in the situation where we derived that this thing is Cauchy. So actually, if we were to find such a function, we would just need to determine what is f of 2, what is f of 3, what is f of 5, and so on. And we need to decide what these numbers are. Okay, so now I will, what? I will say what. So yeah, so let's make some point here. I think this condition here, right, will actually put some restriction on, right? So there will be some restrictions. So
Can we write those logarithms like in the previous problem?
okay. So how will we? Yeah. So let's see. What is the idea here?
Since we got f of x z equals f of x f of times f of z.
Yeah. So okay, we can do that. Yeah. So let's duplicate. So we have a lot of. Let's collect all of our information. So we have this. We have this. We have this. Actually, these are kind of, maybe I just rewrite this. So yeah, f of 1 equals 1, f of y equals 1 over y, and we have f of 1 over y equals, what's that right? Make 1 over f of y. And we have this Cauchy equation. So yeah, so we can take logs. We'll get log of f of x plus log of f of y equals, oh, what did I write? I meant to write this. Log of f of xy. And I mean, yeah, I mean, we can also, moreover, we can write x equals e to the u. I don't know if it's helpful, but we can write, and we can say g of x plus g of y plus g of x plus y, where g of x equals log of f of e to the x. Now, so Kareem, did you have any idea where to go from here?
Wait. Is there any way we can bound it?
Hmm. Yeah, so hmm. So maybe I'll make some point here. So the question here is there such a function, right? So we only have to give one. Yeah, so it might mean that it's hard to find all of them. And also I'll make some point here, which is, so there's two things that can happen, right? So one thing that can happen is, you know, when you get a functional equation, there's like a really not like there's only like all the solutions are very nice, like maybe they're f of x equals x squared or f of x equals x or something. Or it could happen that there's like pathological solutions, very wild solutions. And one point I'll make is that, you know, when you have weird domains like this, and when you have something like Cauchy's equation, but where did we have like Cauchy's equation, but with rational domain, you can really get wild solutions. And so, yeah, so I'll just say that like for this problem, since they're only asking you to construct one solution, right? It's possible that like there's very wild solutions out there. Hmm. So here's what I'll do. But I'll say the way to go from here actually is, okay, we use the fact that it's Cauchy over the rationals. So we really just need to decide what are these numbers? What is f of 2? What is f of 3? And what is f of 5 and so on. And then you can extend it to all rational numbers, f of x. Yep. Yeah, so I'm wondering if I should just leave this for homework. Maybe maybe I'll make some comment which is like let's make some comment like this. So let's maybe analyze this equation here. So what is this really telling us? So I think if you look at f of, I'm going to say p now. Okay. So f of p equals 1 over p. So p is a prime now. What it tells us is, let's say f of p is something like, say q1 to the e1, q2 to the e2, qr to the er, right? So these are primes, and so now ei is an integer, and these are primes. Then f of p is equal to f of q1 to the e1, f of q2 to the e2, and then f of qr to the er, something like this, right? So, and this is 1 over p. So it tells us when we look at these primes, that's what I meant. When I look at these primes q1 through qr, and I look at f of them, all these numbers either need to be 1 or a prime. Does that make sense? Does it make sense what I'm saying here?
I think, yeah.
Right. So like, yeah. So maybe I'll say, uh, or f of qi equals p or 1 over p, right? Okay, and moreover, yeah, and there's some more. There's actually some more restrictions as well. So, like, if it's the case that f of qi is p, first of all, yeah, if only one of the f of qi can be p, and the rest have to be 1. So yeah, we can say it like this.
Why would they have to be one?
Are you, sorry, say again?
Why would they have to all be one?
No, I'm not saying they all have to be 1. What I'm saying is only one. So there's two cases, right? For each I, f of qi is 1, or it's p or 1 over p. And I'm saying the second one can only happen for one of the primes. Yeah, maybe I can just write. So maybe I should write it very. So what I'm saying is, there exists at maybe I can say exactly one I such that f of qi equals 1. Does that make sense? So equals p or 1 over p. That's what I mean. Yeah.
But why?
But so the reason is if there are multiple, then you cannot. I mean it's because I'm looking at this equation. Oh no, actually you're correct. I'm wrong. I'm wrong. No, sorry. What I said is not quite correct. Yeah, you're right. What I said is wrong. Yeah, sorry. This is not true. This is not true. This is not true because there can be some cancellation. No, maybe a better way to do this is this. We should use bijectivity now. F is a bijection, right? Okay, yeah, we should use that F is a bijection. And yeah, so now we use F as a bijection. And then okay, then we know because F is a bijection, each of these can happen at most once. And in fact, we know the first case cannot happen, right? Because F is a bijection. Right, so this case is impossible because F is a bijection, right? So and we already know F of 1 equals 1. Does that make sense? Yeah, does that make sense? So what's the conclusion? So the conclusion is F of P equals F of Q1 to the E1, F of Q2 to the E2, where F of Q1 equals P and F of Q2 equals 1 over P. Yeah. Does that make sense? Abdullah Karim, does the argument make sense?
I don't get why there wouldn't be any other prime.
Because of the bijection property. Right, so there can only be one prime that maps to P. Or,
Oh yeah.
and only one that like there can only be one number that goes to P and one that goes to 1 over P. Does that make sense?
Yes.
Abdullah
But
doesn't. Uh-huh.
okay, yeah, it makes sense. Yeah.
Yeah, so I'm using the bijection property here. So because of the bijection property, you can't have F of Qi equals 1. And then yeah, you can only have one that goes to P, one that goes to 1 over P. And then there's the point that okay, now these exponents should actually be either 0 or 1, right? Because no, sorry, no, that's not sorry, no, that's not true. That doesn't have to be true. Yeah, that doesn't have to be true. But what there's a problem now, which is that if both are true, well, then what? Then yeah, so then what's the problem? Then we have yeah, so if we have both, then from here we get f of Q1. No, but is that okay?
But how can f of p be a prime when it's we have the equation where f of xy equals f of x times f of y. So
So
isn't it
you're saying
Q1?
how can f of P equal a prime?
No, not. I mean, how can in the equation, the in the given equation, not in general,
Uh-huh. So
where Q1 and Q2 are in integers.
you're saying in this equation or in this equation?
No, I mean, yeah, this one.
So this one here?
Yeah, because we have on the right f
Uh-huh.
of xy equals f of x times f of y.
Uh-huh.
So I think I don't get the transition between rationals to positive integers.
Um so sorry, I'm not understanding the question. So is it I guess did this part here make sense?
No, the second one, second equation, f of p equals q1 to the e1 to the
Uh-huh.
no, under.
This one, yeah.
Yeah, this one.
Ah, I see. So the point here is I'm saying f of p is a completely general number, right? And then I'm writing down its factorization.
So here f of p is not a prime.
So p is prime, but then f of p is just some number. I don't know what it
Okay.
is.
But okay, so we assume that f of p is an integer too.
No, it doesn't have to be integer. It can be rational. So I'm allowing the exponents to be negative.
Okay, yeah, okay, okay, yeah, no, okay, yeah.
Now, does it make sense? If I have any rational, positive rational number, I can write it like this uniquely.
Yep.
Right. So yeah. So good. So thanks for the question. Yeah. So sorry if it was unclear. So right. So we're saying f of p is a completely general number. And I'm writing it like this. And then I'm deducing some properties about that number. So I'm saying, okay, it's like this. And then f of p is 1 over p. So actually that puts some restrictions. That means for every one of the primes that showed up in the factorization, f of qi is 1, p, or 1 over p.
But why?
Yeah, but yeah, maybe it's not so. Maybe there's a mistake here. Yeah, now that I think about it, this is not exactly true, right?
But
So
like with pigeonhole, doesn't it like maybe uh like if there are more like so many q like q1 q2 q3 q to the like 10, don't
uh-huh.
they each has to be different?
If
Oh, oh, sorry, I mean at least one of them has to be the same. If the only options are p1 1 over p, so then that contradicts the fact that we have a bijection.
so oh I see. You're saying if you're saying I take all the primes or something, or
In a way, in a sense.
um yeah, so I'm not sure I understand what you're saying, Abdullah.
Okay, so in the red equation in red, right?
Yeah.
So what if f of p could be f of q1 to the e1, f of q2 to the
Uh-huh.
etc., right?
Yes.
But we know that there's a f of p f of x is a bijection.
Mm-hmm.
So if we have f of p is f of q1 e1 until like f of q5 to the e5,
Mm-hmm.
by pigeonhole one of them must be the same, but we have a bijection.
So
No.
so I understand. So we say f of q. So maybe you can just say it one more time. So if you say f of p equals, yeah, maybe you can say it one more time. I didn't. I'll try to
Okay,
write
yeah.
what you said.
So okay, um but I just want to make sure, so we mean the point that so I just want to make sure I'm getting what you're saying
Mm-hmm.
exactly.
Mm-hmm.
So are you saying that f of q has to be either p 1 over p or 1?
Yeah, so now actually I realize this isn't true. Now I just realized this is not actually true because there can be some cancellation. I didn't quite think this through. So
Oh, okay,
um
yeah, yeah, that's where I was getting at. Okay.
yeah, so you're right. I think there's maybe a mistake in what I said. Yeah, you're correct. So I made it, there's something wrong about what I said. Yeah, so let me just, yeah, what I said is not exactly true. Yeah, so let me actually, maybe this is not the correct way to go about this. Yeah, so this is not true. There can be some cancellation. Yeah, so what do we do? Um, So maybe I'll say this here. So actually, I think what I said is wrong. Yeah, so maybe I won't try to. So maybe I'll say I won't try to find all the functions because now that I think about it, I think there are many functions that satisfy this functional equation. What I will say is it's maybe easier to just construct one, and an idea for constructing one is the following. You can say let's yeah, so this won't solve it in general, but remember our goal is only to construct one function. So let's say f of p equals q for simplicity. So there's some prime whose value is some other prime. And then what does it mean? It means that uh, f of p equals 1 over p. So that tells us that f of q equals 1 over p. Okay. So the point is that primes come in pairs where f of p equals q and f of q equals 1 over p. So this is some pair of primes. And then the idea to construct one function, you don't have to find all of them, is to basically partition the primes. So we say the primes they become, so all the primes, you separate them into two lists where you have one which is P1, P2, P3, so on, and Q1, Q2, Q3. So each prime occurs in exactly one list, and then you pair them like this. You say f of pi equals qi, and f of qi equals 1 over pi. And you just do this. And you say this is the solution. So maybe it's an exercise, but you can check this actually is a valid solution. If you just separate the primes into two lists and you basically say this is true, and then you extend by this Cauchy equation. Does it make sense what I'm saying?
Yeah.
Yeah, so I think this, so you can check this will give a valid solution. So actually, I don't know how to find all solutions. I think maybe there are some sort of pathological solutions to this equation, but this is certainly at least one. Okay, so does it make sense to?
Yeah.
Yeah. Okay. Abdullah, does it make sense? Karam?
Uh, could you repeat the thing about the primes?
Yeah. So
The,
what
the
I'm
last part about the primes.
yeah. So what I'm saying is I'm not constructing all solutions. I'm constructing one solution, which is you take all
Yeah.
the primes and you separate them into two infinite lists. Okay. Does that make sense?
And but what is the pattern of separation of the primes?
Are you asking what? How do I do the separation?
Actually, no.
Yeah. So Karam, what's the question?
How can
Sorry, so yeah, I don't understand. So are you asking how I'm doing the separation? So the point is once I separate it completely arbitrarily, however you want. But then once you separate it, you just say, okay, f of p1. So the f of pi is equal to qi, and f of qi equals 1 over pi. Right? So it's this thing that I wrote here. Let me maybe write it a little bit more clearly. So yeah, I say f of p1 equals q1, f of q1 equals 1 over p1. And so on. I say f of qi equals pi f of, or no, f of, okay. Okay, so we lost Karam, but that's hopefully he can rejoin. But yeah, Abdullah, does it make sense, the solution?
Yeah. It does.
Okay, good. Yeah, so maybe for homework I'll send some problems, but maybe you can find more solutions. I'm not sure if it's actually possible to figure out all the solutions. They may be completely pathological ones. So maybe I'll think about it a little bit more. Um, okay, good. So um, great. Yeah. So okay. So I guess that's all for today. Do you guys have any more questions for me or anything else you'd like to discuss?
I don't have anything.